In the previous videos, it was several times mentioned that we are interested in how errors propagate into the estimation results. You already looked into some examples in the exercises using empirical data. Furthermore, it was explained that in this unit we will learn how to determine and interpret the precision of the estimator x hat, based on the functional model and stochastic model that we know. In order to do so, we first need to introduce two important statistical laws: the mean propagation law and the covariance propagation law, which will allow you to apply error propagation. We will present those laws for linear functions only, since we are only dealing with linear or linearized models in this course. Here we see that the random vector u is a linear function of random vector v. If the expectation and the dispersion of v are known, the propagation laws allow you to determine the expectation and dispersion of u. So starting with the mean propagation law. The mean propagation law tells you how you can determine the mean or expectation of u if you know the mean of v as follows. Rather simple, just applying the expectation operator to both random vectors in the equation. Now remember the following example from the exercises, where we took the sum of two independent distance measurements and we are interested in the expectation of this sum. Let's first write the sum of the two random variables in the same form as we used to present the propagation law, which is shown here in the bottom right of the slide. So in this case, u is the random variable, being equal to the sum of y1 and y2. Matrix L is a row vector with 1s, and v is the column vector with y1 and y2. There is no deterministic vector c in this case. We can apply the propagation law in the bottom right, where we see that the matrix L, the vector with 1s, must be multiplied with the expectation of v. If we elaborate on this result, it follows that the expectation of the sum of two random variables is simply equal to the sum of the expectations of the individual variables. Knowing that these are equal to x1 and x2 respectively, this gives the final result. Let's now look at the covariance propagation law. Again, we start with the general form of the linear model. Let the expectation and dispersion of random vector v be known. What is then the dispersion of u? Well, it is given by the equation as shown here, showing that it depends on the matrix L and the dispersion of v. Vector c is a deterministic and consequently has no influence on the dispersion of u. Remember that the dispersion is equal to the covariance matrix. Therefore, we can write the covariance propagation law also in terms of the corresponding covariance matrices of u and v. Applying this to the same example as before, we now need the dispersion of the observation vector. And since the observables are independent, this will be a 2 by 2 diagonal matrix. The linear function we are looking at was the sum of the two random variables. We can now apply the covariance propagation law as shown in the bottom right. The covariance matrix of u is thus equal to matrix L multiplied with the covariance matrix of v multiplied with the transpose of L. We plug in the covariance matrix of v and we get this expression. Feel free to pause the video now to check the following result, showing that the result is equal to the sum of the individual variances of y1 and y2. Remember that you also obtained this result in the exercises. And also remember that the result changes in case y1 and y2 are not independent. You will see that again in the exercises. In this video, the linear, mean and covariance propagation law were presented. Knowing the expectation and covariance matrix of V, we can now determine the expectation and covariance matrix of a random vector U, which is linearly related to V. Time to come back to the question, how to determine the covariance matrix of estimator X hat. Knowing the functional model and stochastic model of our estimation problem, the answer is that we need to apply the covariance propagation law. In our case, the expectation and dispersion of the observable vector y are known. The best linear unbiased estimator, by definition, is a linear function of this observable vector. The function is shown here. In the exercises, you will apply both the mean and covariance propagation laws to firstly derive that indeed the expectation of the estimator is equal to the true x, and secondly to find the covariance matrix of X hat. And then in the next part of this unit, we will start looking at the interpretation of the covariance matrix or precision of X hat.